in size is 24 square. Okay. So the larger truth calculus is 24 square degrees. So this is a tiny region of this truth calculus we are simulating. And we also have the web page where we have more information for you. So what is AGILE? It's a pipeline, it's a software, it's basically the batteries included solution for this kind of a simulation. And it has 4 main ingredients. So these 4 boxes on the slide, where we go from the left to right. So we simulate the underlying truth catalog. So we create it from scratch. And then we add in, on top of this static truth catalog, we add in variability for AGILE, for stars. And then we feed all of this into our image simulation pipeline, which takes care of simulating the images. And finally, the last box is about extracting catalogs, so analyzing the simulated images. So the truth catalog that we have is empirical in nature. We have 3 populations of objects. So we have the galaxies, obviously we have the AGILE, and then we have the stars. For the galaxies, we start with a complete population of galaxies, starting from the Cosmos 2020 stellar mass function. We use this external code called EGG in order to give us a complete galaxy population with morphology, with typical galaxy properties that you would find in a mock catalog. So on top of the galaxies, we paint the galaxies with AGILE, again according to empirical relations. So we give them accretion rates, we give them optical UV properties, we give them SEDs, and this is how we get an AGILE population. I want to also mention that we have black hole masses, and you should tune into the talk of Daniel Robertson on Wednesday to hear more about the continuity equation, how to do this in a self-consistent manner. And finally, we go to another external simulation. We fetch in the stars from Milky Way and the Magellanic Cloud. So this is another in-kind contribution within LSST, and we just put this into our truth catalog like that. About the variability, we have basically 2 different objects with variability. Most important, we have the AGILE. So each and every AGILE in our simulation is giving a damped random walk light curve with parameters varying from AGILE to AGILE. So all of these light curves, they scale with the physical properties of the AGILE, namely the black hole mass, the AGILE luminosity, and then the rest frame wavelength. So each and every AGILE in our simulation has a unique 10-year light curve, which we can then use to generate the images. And for the obscure AGILE population, we have another recipe, and you should tune into Demetra's talk later this afternoon to hear about that. So apart from AGILE, we also have the stars. So we have long period variables, so we have C fates. We have also the variability recipes for this, and then binary stars. So this is something that we added in as well. So what are we simulating? I mentioned 1 square degree in the Cosmos Deep Drilling field, worth of 1,400 visits, more or less. We are using a modified version of the baseline 4.0. Basically, we're skipping some observations so that we can keep the same cadence. So we can keep the 3-year worth of observations, but we don't get exhausted with the data volume. So we are simulating less visits, but with the same cadence over the 3 years. How does this compare to some existing baselines? So here on the left, I'm showing the observations done in the data preview 1 in the extended Chandra Deep Field South. So that's basically half the visits compared to our simulation. And then compared to, for example, the recently proposed ocean deep drilling field strategy, the first 3 years Cosmos is basically the same. So it is basically consistent with what we have simulated in our data release 1. What about the images? We have the raw images. We are using another software called IMSIM to generate the raw images. So this is where you simulate each detector of the LST cam, instrumental noise. There is the atmosphere, all the systematics that you would assume that are there. And we have a set of 30,000 raw images that we start with. And then we add in the raw images into LST science pipelines in order to do the calibration, reduction, analysis of the images, and this is what gives us CalExp images or calibrated exposures. And another set of 30,000 calibrated exposures is something that we have currently. Then we stack the single visit images together to get the deep coordinate images, and this gives us about 2 magnitudes of increased depth. And this is for the first data release. This is the largest single piece of data volume that we have. This is about 3 terabytes worth of images that we have. So we keep on going with the LST science pipelines. Now we feed the images directly into the science pipelines, and then we do the source extraction, basically the analysis of the images. And this is the catalogs that we are releasing. So we have the source catalogs. This is one catalog per single visit image, 30,000 source catalogs, no problem. We have the object catalogs. So you go to the deep coded images, and then you do the source detection, the photometric characterization. So this is like one single deepest catalog that we have. It's about 250,000 sources that we have. Then you take the object catalog, and then you go back to the single visit images. You do forced photometry on each of the single visit image at the position of the objects that you measured. And this is basically how you can get a light curve for all the different objects. So you go do forced photometry in the single visit image at the location of the object that you measured. And finally, to close it all together, we have the matches between the truth catalog and the object table. So this way you can go to the object table, and you can ask, okay, what was the actual object that was responsible for this detection? So you can put one-to-one together. This was an AGN, this was a galaxy, this was a star. And all of this was about 300,000 CPU hours worth of running. All the images, all the catalogs. And this was a proposal that we are now completing at Pleiadi. Okay, how do you access the data? So we have the 3 terabytes of images. This is a little bit cumbersome to download to your computer. Also, we have the catalogs. So we put together a master database for all the catalogs that we have. This is more than 100 gigabytes of data. And the outcome, so the end product, we have a data model that is very close to that of DP0 and that of Deep Data Preview 1. So basically, with AGILE, as with the real data, you can use Butler to do the image queries. You can do catalog queries with Butler. And then we have this database solution, which is mimicking the database solution of the real data previews. So we have this database solution that you can do actual queries on catalogs as well. And so all of this data is currently stored in this cluster called Ad Hoc Newton, which is in Naples. And this is the preferred way that we are suggesting people to access this data set, especially the images. The catalogs, you can probably download them to your own server, but the images, 3 terabytes, is a little bit cumbersome. So we have this solution to store them in the Ad Hoc Newton computer, and you should be able to request an account and access by VPN to this cluster if you would like to work with the data. So what about the applications of our end-to-end simulation? So there's plenty of applications immediately possible. So you can start doing AGN selection. You put everything that we have in the simulation. You put the truth labels, and then you can see how good you are at selecting AGN. You can do variability analysis. You can do photometric redshifts. You can look at the morphology of the AGN. And we have compiled this Google document where you can put your own ideas. Let us know if you want to do something, and we can talk about how to do it. One immediate application that we are looking at in the paper in prep is to have a look at the flux definitions. So the flux accuracy, how well you are recovering the flux of different sources. So you put the truth flux on the X, you put the measured flux on the Y, and then from the LST science pipelines, you have different flux definitions. So for example, PSA flux or an aperture flux with a fixed aperture, or then the C model flux. So we can look at different populations of objects, for example, stars. You can say that, okay, PSA flux is performing the best. For galaxies, C model flux. Then you can look at the type 2 AGN, which are basically obscured, so they behave like galaxies. So you see the same biases that are present for the galaxy population. And then for the type 1 AGN, it's interesting to see that if you split the population into two, so if you split the population into host-dominated systems and AGN-dominated systems, so you can see when the AGN is a subdominant component, you can see PSA flux, you get a little bit of a bias in the record PSA flux. But this is a quantification of the flux accuracy of what you get from the science pipelines for different objects. So another thing that you can look at, you can take an AGILE selection from the literature. So this is a Krum like selection from 2009. So you select bright and point-like objects, and then you do multiple color cuts, and then you just compare the numbers of retrieved objects. So basically you can use AGILE to get these two numbers, the completeness and purity of your selection. So how many true AGILE you're recovering, and how many non-AGILE you're recovering with any kind of selection. And this is just an example. With the real data, I presume that something more complicated with variability is included, but in principle you can use our simulation to derive these two numbers. So in addition, so we compiled a list of notebooks. So in order to access the data, in order to explore the data and play around with it, so we compiled a series of notebooks which highlight different aspects of the data products that we have. So for example, we have a notebook which is comparing the first data release of AGILE to that of the data preview 1 in the extended generative field south. So one thing that we explored is yes. So we looked at the sky positions. We found out in AGILE you have the bright stars giving you some masking in the survey, but we also have some dense regions of galaxies that basically make the pipelines confused, skip the deep blending, and then skip these objects completely. And this is something that we also found out that if you look at the globular cluster in the data preview 1, it's also there. So you don't. So two objects that are too complicated to deep blend are just skipped. And this is something to like a gotcha for the real data when we're working with it. Okay, I will just show in the same notebook we have color diagrams. So in the 6 LST bands, you just plot color diagrams between our simulated data and then the actual data. We just did this as an internal validation, have a look at where we are, and we are doing a pretty good job in actually reproducing what is there in the observations. Okay. But with the truth catalog, we can actually put also the labels into this kind of a plot. So we can say, okay, here are the AGN, here are the galaxies, here are the stars. Okay, we have another notebook about the images, showing you the images, where are the sources detected in the images, doing the same with the co-added image. And so this is everything that we're releasing together with AGILE. So I will go to my conclusions in the interest of time. Okay, so we are releasing the first data release of AGILE to each and every one of you. And the next steps, so we are finishing the paper in preparation, which is also to be circulated with the AGN Science Collaboration for your comments. And we have a link application ongoing for the further development of AGILE to add in features or wherever we want to take it. And as I mentioned, there are many possible applications with AGILE. One thing that we're already working on is with the lensed AGN working group, trying to find AGN in lensed images, which is led by Henry West. And what we have built, we consider it to be a living project. So I would like to have a discussion where to take it next. So we did the data release 1. What is next? So do we want more area? Do we want more depth, more features, cutout images? Anything. And we have a web page. The project document is right over here. And then finally, for the data access, you should check the link for the ad hoc Newton. So I stop there.
Questions? Yes, Gordon, go ahead.
So, I mean, this is fantastic. You're not going to use another 300,000 hours to generate more area, but like, what are your thoughts on cloning or something like that to generate sort of more area? So like, for example, let's say I want to put that 24 square degrees or 1 square degree behind the LMC.
Behind the LMC. Yeah, we are just limited by computational power. So if we get the 300,000 core hours somewhere, is not.
But I mean, I think you need to rerun everything, right?
Yes.
You sort of need to add a small.
So you would like to add extinction?
Yeah, different extinction and a tiny bit of error, right? The same.
Yeah.
Parts.
Yeah, I mean the catalogs that we are providing, they have the array coordinates and they have the measured fluxes. So basically, I think it's completely possible to just say, okay, we transform it here. We take away the rendering from Cosmos and we put in the rendering from LSST. I think it's possible, but I don't know the details of this exercise. But I think it's.
Other questions? Yes, go ahead.
Make sure that he doesn't say.
Here.
What IGM model do you use for the Lyman alpha forest?
For the Lyman alpha forest.
Yeah.
So specifically, we don't have. So we go up to redshift 5.5, and then what we do is we have the accretion rate distribution of AGN, which is basically constrained up to redshift 4. So after redshift 4, we are basically extrapolating the data a little bit. So from 4 to 5.5. Okay. So we don't have a specific. We have the IGM model at higher redshifts, yeah, which we are including, but we don't have a specific population at a higher redshift.
Okay, so at the lower redshifts, you're basing it off of data and not a model.
Yes,
okay,
it's all empirical.
And so above redshift 4 is
yeah.
a model. Okay, thank you.
Yeah.
Other questions? Yes.
Hi, nice talk. I would like to ask, how are you accounting the variability when you do stacks?
How are we?
How are you accounting for the effect of variability or the uncertainty that can happen due to the variability when you do stacked images?
This is an excellent question. It's a question the science pipelines. So when you do the stacking, I'm not sure which statistics you're actually applying on top of the stacks, but it's basically a question of the stacking, because then after that, basically after the stacking, you are back to static images that you're analyzing. So it's a combination. It's a combination of all the measurements that you get from the individual points.
Okay, thank you.
Any other questions I'm not seeing? Okay, well, thank you. Let's thank the speaker.
Thanks. What is it? Oh, yes. Excuse me. No, sorry. Oh,
Okay.
Okay, so we will now hear from Elham Saremi, who will tell us about the LSST-IR fusion pipeline.
Yeah. Hello, everyone. I'm happy to meet all of you. I'm Elham Saremi from Southampton University, and I'm going to speak about the LSST VISTA fusion data pipeline, a tool that is great for various scientific projects and including agents. Fortunately, all of my collaborations are here. Professor Manda Banerjee, I guess she's online participation, and you can see there Raphael Shelley Tang, and Richard. I'm not sure. Oh, sorry. Professor Richard McMahon from Cambridge University. Yeah, let's start. Okay. As all of us know, LSST is a large survey optical telescope will run for 10 years. And because LSST scan again and again, it's very nice for AGNs based on their variability. And we expect to find millions AGNs from LSST. And we can create the SED of objects based on the six band optical of data. But as you know, sometimes the agents or other objects are hidden based on the dust. And so the other wavelengths and especially the near IR is very important for these objects, for finding these objects. So the Visible and Infrared Survey Telescope for Astronomy, VISTA, is designed for a large sky survey. And this is a 4-meter telescope, 4-meter telescope and a wide telescope. As this is in the Parnell Observatory, VIRCAM. It's a VISTA infrared camera with 16 detector and a wide field of view around 165. VIRCAM had many various surveys over 10 years, but now is retired and replaced by foremost spectrograph. However, the legacy data of VIRCAM in all of surveys is very useful still for many different scientific projects. As you can see here, we see the optical bands of LSST and near IR bands of VISTA, and this is very clear. All of bands in optical and near IR together are complementary of each other and this is very useful for many science. A K-band survey, especially in K-band is very important because a K-band survey can construct a comprehensive picture of the galaxies in the early universe, detecting galaxy at a high redshift and redshift higher than 2. It's very usual in K-band because of the dust and older star. Detecting these galaxies in other bands is not very possible. So this is a main point for that the near IR band are very important for LSST science now. From other side, both of VISTA and LSST cover most of the southern hemisphere, and this is a key point for us to use these pipelines, this fusion pipeline between the LSST and VISTA. You can see the coverage of most of the surveys of VISTA will come here, and for the LSST at that figures. Over the years, VISTA had mapped most of the southern hemisphere with different surveys with different goals and different depths. For example, the main survey of VISTA, that name is VHS, it is a wide survey of VISTA in the 2J and K band, and this is 30 times deeper than 2 mass, and this covers most of the southern hemisphere. Another one is Viking, and another one, for example, is Video, that is very famous, very deep survey of VISTA in the 5 near IR bands for a study of the extragalactic high redshift clusters and galaxies. Or, for example, another one is KDFS. It's a K-band survey of Euclid deep field south, or fifth deep drilling field of LSST. So thanks to all of VISTA WIRCAM surveys, we have a great NIR data in the Southern Hemisphere. Okay. As you know, LSST Science Pipelines is very nice pipelines for using the raw data from Rubin Observatory and processing all of them for creating the science-ready catalogs and images for all of the goals of LSST. The main point or main thing in the LSST pipelines is the adaptability of this and flexibility. So we can use these pipelines for other telescopes. Because of this, we use these pipelines for VISTA WIRCAM images for processing of data. Just because in the NIR we have some complexity of data, first we use the Castle pipeline, the standard pipeline of WIRCAM, for pre-processing of data, and then we use the LSST pipelines for processing of the final processing of data and creating the images and force photometry. For using the LSST pipelines, thanks to Rafael, we have two repositories that names is OBS-VISTA and LSST-IR Fusion. OBS-VISTA allows us to use all of VISTA images processing by LSST pipeline, and LSST-IR Fusion handles all of processing data, and the output of these pipelines is similar to the LSST pipeline, is CCD calibrated images, deep quad images, and force and measured catalogs in all of VISTA and LSST bands. As a prototype, we use the hypersuprime CAM data instead of LSST for test of the pipeline. For that, we use the HSC strategic program that this survey is processed by the LSST pipelines. And so this is a good test for our pipeline. We have fortunately, this program of HSC have coverage some fields of VISTA, for example, the video Viking and some part of VHS. So we tested the pipeline with HSC data. And for example, you can see a ultra deep HSC program coverage the video part of the video survey of the VISTA. So the result of this test now transferred to the UK DAC Center, UK Data Access Center, and you can easily use these results in the UK RSP. And similar to US RSP, here we have some Jupyter notebooks for using and for knowing how you can use the deep quad images and catalogs, multiband catalogs of this. Okay. We started some scientific projects with the result of the now HSC VISTA Fusion data and then LSST VISTA Fusion data. Okay, ready for using the LSST VISTA Fusion data. Now we are starting with the HSC VISTA Fusion data. For example, about the AGN fields, we are developing a 2D image analysis for studying the Haas galaxy properties of low redshift AGNs. this project is led by Shenli, and Shenli speak more about that in his talk. But just for summary or briefly, I can say we selected the one sample from Burke et al. For dwarf AGN based on the optical variability, and we selected one field of the video survey of VISTA that is coverage with the deep field of this. And after the sampling some of data, we use the NIR and NIR VISTA data and HSC result of the HSC VISTA fusion data for this work. I guess Shenli shows you how NIR can construct the SED for these AGN samples. And another example is about the decomposition of the host galaxy and analysis of K-band image of one quasar in redshift 0.6. You can see after using this pipeline, we have the data-based model and residual of the data here. I guess Shenli can explain this more. And another project is about estimating the photometric redshift that is led by Raphael. And as you know, accurate photosets are essential for all of LSST science, but it is obvious 6 optical bands is not enough for this. And so NIR data can help for this. Maybe we can hear about the LFR code and estimating photoset in our data in the near future by Raphael. Yeah, and we can hear from this more from Raphael. And another project not directly related to this meeting, but about estimating the total stellar mass of the local dwarf galaxies. You can see we tested, for example, here for one dwarf galaxy, and after estimating the total stellar mass, we can see the preserving the edge of galaxy is much better here in the LSST VISTA fusion pipeline, and we have a higher total stellar mass here. Finally, we are ready to use the LSST VISTA fusion, data fusion pipeline for DP1 data. From the DP1 data, we selected the extended Chandra deep field south for first test, and we are ready by updating the pipeline based on the last version of the LSST pipelines, and the pre-processing of the data of video data is ready. So just we are waiting for transferring the data from US to UK for testing the pipeline with DP1. Thank you so much.
Do we have any questions? Yes.
I have a quick question about the, I think, last project you mentioned, where you calculate the stellar masses of dwarf galaxies and you find improvements. Is this based on what kind of data, first of all? Okay,
this is a video survey of the VISTA K-band data, and this is for example, here is one example. I compared the result of our pipeline, LSST VISTA data fusion, with a standard pipeline of that used for video. Okay, so I can.
Yeah. So the next question is like, do you have also black hole masses for these dwarf galaxies and how the?
No, it's not related to black
okay.
holes. Yeah, just it's about the better estimating the total stellar mass based on the preserving the edge of galaxy.
Thank you.
Just I want to show the result is good also for the other projects. Yeah.
Other questions? I had one I can ask. So, of course, in the deep drilling fields, Fan Zhao at Penn State has also selected dwarf AGNs, and based upon tractor SED extraction, has done his own detailed SED fitting. Are your stellar masses consistent with the ones he's previously derived?
About the SED fitting, Charlie's experience about the agents, but this is about the just local galaxy and is not related to the SED fitting. Estimating of the total stellar mass is not based on the SED fitting. It's based on the another method based on the theoretical models.
Sure.
Yeah.
Sure.
And estimating the
That's fine. Yeah. So I understand your method is different, but are the results from your method consistent with the results that have been derived previously?
Yeah, the result is now is different, but we are in the start of this work. Yeah.
Okay.
And this is the
Okay.
First result for test. Just.
Okay, that's fine. Well, this could be another useful comparison to try.
Yeah.
Yes. Matthew, do you have a question?
Yeah, thanks. I was just wondering if we know when the US to UK data transfer is going to happen for DP1?
More likely August.
August. Okay, so it's okay.
Okay. Any final questions? Okay. Well, let's thank the speaker. And as you've probably noticed, the talks were deliberately put in sort of random order. So now we're jumping around from one topic to a next to another, all of which are very different. I think Chris Doan will speak next and will tell us about her variability investigation.
Yeah, sorry, I'm gonna have the mic. So, thank you. Okay. This is like that. Put that on there. Okay, great. So now for something a little bit different. Once we've got this amazing data from LSST, what are we going to do with it? So I'm going to talk about how we can use, continue to share. Where's my, where's that gone? Good. So I'm going to talk about what we're going to be able to do with the data when we've got it in hand. So I really want to understand what the accretion flow around AGN is actually doing. What's it physically doing? And I want to understand it for its own sake, but also we know that that accretion inflow powers outflows, jets and winds, and they do AGN feedback across cosmic time, sculpting the growth of galaxies. So this is stuff we need to understand. And black holes, they're meant to be the simplest possible objects. There are only 3 fundamental parameters that they can have. There's mass and spin. Charge they're not going to have astrophysically, but we see them via the accretion flow, so we've got the mass accretion rate coming in through the accretion flow. There are 3 fundamental parameters that determine what this accretion flow is doing. How hard can this be? Yeah, we've been looking at this for 50 years, and it's really rock hard. Maybe there are some second-order effects as well, but there are these 3 fundamental parameters. Spin is very controversial, and we still don't have a great grip on. So there's at least 2 parameters that are very important in AGN. They have a huge range of mass, from 10 to the 5 to 10 to the 10. So we have to think about them as a 2-parameter family, not just a 1-parameter family. And we get a bonus set. The universe has actually been kind to us. The stellar mass black hole binaries in our own galaxies, give us a nice little training set on what accretion looks like onto a 10 solar mass black hole, roughly. They're all within a factor of 2 of the same mass because they all arise from core collapse supernovae. And maybe they all have similar spins because of that. So really, in the stellar mass black holes, there's only 1 parameter. and that's mass accretion rate. And so we can use these as a training set. And when we use them as a training set, what we see is that there's a dramatic change in the accretion flow. And if you change the accretion flow slowly, it happens at around 1% of Eddington. And there's this huge change in the spectral energy distribution, where it goes from the red line, which looks like knows at least something about an optically thick, geometrically thin accretion disk, to the blue line, which is really nothing like an optically thin, geometrically thick accretion disk. And so the easiest way to interpret this is that it's not a geometrically thin, optically thick accretion disk. It's one of these hot flows. Advection-dominated accretion flows are the most famous version of this, radiatively inefficient accretion flows. And they give you a very clear upper limit to the accretion rate. When they become optically thick, the coupling between electrons and ions gets very efficient, and they collapse into a one-temperature flow, which puts you straight into the accretion disk solutions. So this gives us both a way of interpreting the spectra change and also a way of understanding that transition luminosity, which is quite well defined when you do it slowly. Some non-steady state nastiness if you go too fast. So now let's scale this up to the accretion flow in active galaxies. What would we be looking at? Well, plasma physics just scales, so nothing really changes for those hot flows, for those advection-dominated accretion flows. But accretion disks, they know about black hole mass. They know about a size scale. As we go to higher black hole mass at the same Eddington fraction, that disk temperature drops. So if we were doing a kind of generic 10 to the 8, 10 to the 9 solar mass black hole, what would our scaling of those spectra look like? Well, it would look something like that. We'd just drag that disk down into the ultraviolet, and that's what we should get. So if this is happening in AGN, then at around a few percent of Eddington, there should be this dramatic transition that's mainly about that UV. And if the UV drops, then the broadline region's going to notice. And so even if the broadline region itself still stays there, the ionizing flux has just dropped through the floor. So there's going to be a huge drop in the visibility of any broadline region. So this is predicting that actually there should be some true Seyfert 2s in there that not obscured, they just don't have UV, and they don't have then a strong broadline region as well. And when you look at the demographics of SDSS quasars, so this is just stacking in a 2-parameter family, so it's black hole mass along the x-axis, UV luminosity along the y-axis. And you just look at the demographics of where we see these blue broadline region objects, and they're very clearly, the majority of them, there are thousands and thousands and thousands, sort of between 10, 20, 30% of Eddington. As soon as you start going down towards a few percent of Eddington, instead of having hundreds of thousands, you've got tens. And their spectra don't look particularly convincing either. But then it's all, but they're reddened, there's host galaxy. Yes, indeed, there is, and it gets tricky. So let's think of new ways of getting down there. So one of the nice recent things has been the eROSITA All-Sky Survey. It's a soft X-ray telescope. And if we select unabsorbed X-ray sources that live in the centers of galaxies, this is Scott Hagen's work, then you have a very clear identifier of AGN activity. And then this is also in a region, the EFEDS region, where there's good galaxy imaging, so you can subtract the host galaxies, and that separates out the AGN nucleus from this host galaxy component. And then you get this, again, it's a 2-dimensional set. There's a range of black hole masses and a range of near UV luminosities that you get. But if you just stick in one black hole mass range, so we're looking just at black hole masses around 10 to the 8 solar masses, and then you can stack their spectra and see what these do as an ensemble. And what you see very clearly is that at the brightest UV luminosities, you see something that's clearly got this bright blue component. It's got soft X-rays. You go down in luminosity, you've still got that blue component. Down, 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 and now the optical UV is looking kind of flat, and then suddenly it switches to something very red. The X-rays are now quite hard. And this is happening at around 1% of the Eddington limit. And this is telling us that there's a transition in AGN spectra in just the same way that we're seeing it in the galactic binaries, that there's something fundamental about the accretion flow at this kind of luminosity. I've just put the UV on there as well, just so you can see that Galax shows this too. And now that there's DR18 of SDSS, you can see how much the broadline region is responding. These are unobscured X-rays. And so this is not reddening that is causing that H beta to be narrow. So that's on stacks. That's telling us about the population as a whole. This is hardwired into the population as a whole. But you can also see it in individual objects. These are the changing look AGN. And so in the optical, you'll be seeing this kind of 10% up, down. And then some of them just kind of do a bit of a nosedive. This one over the course of about 4 years did quite a strong linear nosedive in optical luminosity. And with broadband UV and X-ray data from space, you can see what happened. You can see that when it was bright over here, it had this strong blue optically thick emission down into the soft X-rays and hard X-rays. And then as it came down, the UV collapses. The X-rays are still moderately strong, but the UV has collapsed. And with it, the broadline region has gone as well. So this is telling us not only do we see it in these rare individual changing look AGN, but we also see it in a population as a whole. But if we've got samples of variability, then this is the SDSS stripe 82 photometric variability. The amount of variability we see is obviously going to be amplified at the changing look transition. And this is the amount of variability from SDSS stripe 82. And you can see very clearly that there's much more variability in these low Eddington fraction AGN. So if we want to go look for changing look AGN, then monitoring these low Eddington fraction broadline AGN, at some point they'll probably just go up, go down, go up, go down, and slide over the changing look transition. So monitoring a sample of these and looking for features in their variability that tell us about this different state coming in, that would be really interesting. But even above the transition, we've got huge problems in AGN. Above the transition in the stellar mass binaries, it's like a disk. It looks like a disk, it varies like a disk. Above the transition in AGN, it doesn't. It varies too fast, and it just doesn't look like a disk. So let's have a look here. These are all broadline AGN. They're all the same mass, roughly 10 to the 8, and they're spanning more than an order of magnitude in luminosity, spanning more than an order of magnitude in Eddington fraction. The broadband SED going from optical UV X-rays is not constant. It is changing a lot. That's going to have impact on what the broadline region does. And the key thing that you're seeing here is that as you go to higher Eddington fraction, this disky thing becomes more prominent and the hard X-ray spectrum steepens. So let's look at one of these in more detail. We'll look at a completely standard AGN spectrum. And you look at this, here's the optical UV, and soft X-rays, hard X-rays. And you think, but it does kind of look disky down here. Isn't everything okay? No, everything is not okay. A disk down to the last stable circular orbit, like we see in black hole binaries, would look like that red line. What we're seeing does not look like the red line. It dips down in the far UV. And also, when you do this in black hole binaries, when you're looking at the accretion flow past the transition in black hole binaries, the hard X-rays are always kind of pointing down to higher energies, okay? Whereas these are pointing up. And below 1 keV, there's this upturn. So life would get easier if we just joined the dots. But if we just joined the dots with this warm Compton component, then we're saying that the bolometric output is dominated by a component we don't understand. That's not necessarily good news. So we can try and model it and use models that conserve energy. So we'll just have a constant mass accretion rate like in a disk, but allow it to be emitted in any form that it likes. So it can be black body, it can be warm Compton, it can be hot Comptonization. And when you do that, when you fit it to these data, what you find is something a little interesting, which is the X-ray luminosity always comes out to be around about 2% of Eddington. Not 2% of the bolometric, but 2% of Eddington. And then you can estimate the radius over which you need to accumulate the accretion power, and that radius is going in. So this gives you a way of understanding the much steeper spectra. If you're at 3% of Eddington and you're putting 2% of Eddington into your hot Comptonized accretion flow, you don't have very much energy left for the UV. So your spectrum is very hard and your UV is roughly about the same level. If instead we're at Eddington and we put 2% of Eddington into the hard X-rays, there's 98% in soft X-rays, there's a lot of Compton cooling, and our spectrum is soft. And so we can put that together into, oops, I did not mean that. We can put that together into these models. Okay, did that hit the share button? It did hit the share button, didn't it? Right, did not mean that. Let's go back. So you can put this together into models of what the accretion flow is doing. And continue to share, yes. And you can get a picture that describes this changing spectral shape as a function of both mass and mass accretion rate. And it's these sorts of models that I really want to test and to try and understand something about the physics, what's going on in the accretion flow, both above this amazingly distinct spectral transition and below. Because the spectrum's changing, the way in which the broadline region responds will be different. Let's think about what impact that has on measuring black hole masses as well. Okay, so given the time, I will end it there. Thank you.
Any questions for Chris? Yes, go ahead.
Nice talk, Chris. Thanks. There are about 1,400 changing look AGN now known.
Yes.
So that gives you about 1 in 1,000 of the ones we have. And I mean, they're not all at 0.1, 0.01, 0.02 Eddington. So something else has to be going on to explain those.
I think a big problem is what people are defining as changing look AGN. So if you're looking to see a change in the broadline region, I think you should be defining it as a much bigger change in the broadline region. how do you define a changing look AGN? I would like a broadband continuum spectrum, and I would like to see it go from something like this to something like this. Yeah. So if it does that, I would call it a changing look AGN.
No, I agree. I mean, the problem is the definition is based on H-beta ratios and change on that. And that could just be some more sophisticated breathing rather than anything. And
there is variability everywhere across this diagram. There is significant variability in AGN, and that's why these new models of the accretion flow, where it's not a disk, it's this warm Comptonization region, it's varying faster than a disk could possibly ever vary. It is not a disk. And understanding the structure of this thing that's dominating the bolometric luminosity energy output would be a really good idea. But yes, there's variability all over this. And if we see variability in the optical UV, then the broadline region is going to change. And quite where we define the changing look transition, I think, is a big problem.
Other questions? Yes. Well, I'll just so to take that one a little bit further, perhaps. So, Chris, what observing program would you like using Rubin data, perhaps combined with something else, to provide you with the AGNs you like, turning it into practical observations? Yes. How would you propose to actually get this done?
So, you said it was 1 in 1,000. I bet if we monitored these ones around here at a few percent of Eddington, I bet it would be rather more. And so doing a monitoring program, selecting the ones that are close to a few percent of Eddington, and doing spectroscopic monitoring and or doing swift monitoring so that we have the broadband spectrum. And if we did a sample of those that just sat on this few percent of Eddington, then I think we would understand a lot more.
Yeah, well, Rubin will automatically give you massive samples, so you could go and select things. So you want to look for things in that diagram that are close to that boundary, and your prediction is as you change more. Okay. Yes. Something to do. Okay, please.
Suppose an AGN is undergoing a transition from 1 to 2. So do you expect a large variability in continuum as well?
So there is large variability in the continuum when we see this changing look transition. But the problem is that the host galaxy sits under there. So that's why understanding and being able to separate out the host galaxy in the LSST data is going to be so critical to digging around in some of these transitions.
But how much host galaxy will affect the variability?
How much?
The host galaxy will affect the variability.
So it will suppress a lot of the variability. If you're looking at something that's composite, this is constant, this is varying, and so there's a huge dilution of the variability as your AGN drops. And yet already from SDSS we know that we see, even despite this dilution, we see more variability down close to this transition. And so this is really telling us it's quite dramatic. And if we're able to model the host galaxy and subtract its component much more accurately, then we'll really actually get a much better handle on how much the variability down here is really changing.
Thank you.
Any other questions? Oh, Paula, go ahead.
In the old days, hey Chris, there was a LX over L optical relation, kind of Zaris and Chris, like LX to is that consistent?
Yeah, look at this. So this is what the shape is doing. Okay, from current slide. There's a very clear evolution in alpha OX, which is a horrible thing, and it's misnamed as well because it's actually alpha between the UV and the X-ray, not the optical and the. But anyway, it's obviously capturing something of this. So you can see that as the luminosity is increasing, because I've got constant mass, that's Eddington fraction increasing, this optically thick thing that doesn't fit very well to disk models, this comes up The X-rays are getting steeper, but their luminosity is much the same. And so the alpha OX is getting steeper and steeper, which is something that was noticed a long time ago.
Okay, well, let's thank Chris. You're good. Okay, so we will now hear from Gordon Richards about LSST AGN selection and the relevant unfinished business there. Thanks.
Okay, thanks. First, I just want to say, for various reasons, I think I haven't gotten anything done on LSST in the last 2 years since the Charlottesville meeting. You know, but a lot of other people have, and so I'm going to try to highlight some of their work. And then, you know, related to that, I just sort of want to emphasize, like, if you're thinking like, oh, Gordon has that covered, Gordon does not have that covered. So use me as a resource, and I'm happy to, you know, collaborate with you, right? Okay, so first, just a reminder of sort of some of the numbers that we're dealing with. You know, really only sort of tens of millions of quasars that we're going to identify with LSST data alone. You know, but probably 300 million detected, maybe 100 million with multi-wavelength data, right? And so one of the things that I think as a group we should really emphasize is like what we can be doing to help the Galaxy science collaboration. We need to be, you know, removing contaminants from their sample, and maybe that's a way for us to, you know, generate funds and you know, things like that. Okay, so from my point of view, you know, there's a few things that are going pretty well, right? So lots of work going on with variability based selection, you know, Paulo Sanchez and others. You know, my worry is that there's a lot of things that, like, that's really not going to be the way to go, right? So we're going to find lots of things with variability, but maybe not everything. Reverberation mapping, lots of people are working on that. That's great. Multi-wavelength stuff in the deep drilling fields, Neil and his group certainly have that covered, if not others. Broad, wide, fast, deep selection, I would say not so much, right? Not really as much going on as there should be. So, for example, this nice paper by Story Fisher last year using the Gaia data. You know, we should probably have been making selection function maps probably 2022, right? We're I would say at least 3 years behind that. We could have been producing, you know, catalogs of objects based on existing data. Again, I would say we're at least 3 years behind it now. There's no reason why we couldn't have basically LSST algorithms in place and applying that to new data. The stuff that Akke was showing earlier, I think will help, you know, a lot with this. But again, you know, just in a small area, we need to basically scale that up to much bigger areas. For selection, I still am a big fan of sort of the basic transfer learning construct, some kind of autoencoder to basically take the high dimension feature space down to a lower dimensionality latent space. You're going to do your clustering in that latent space, and then your selection in that latent space. And so, you know, as an example, like the Bovie XDQSO paper in 2011, that was very sort of novel idea at the time. They were kind of just using Gaussian mixture models to describe the data, and there's not really a good figure, but I was trying to find one. And so that always really bothered me. I'm like, okay, that kind of makes sense, but it disturbed me a little bit because they're using this Gaussian mixture model in real feature space. And I think that's a huge mistake, right? And they were able to do it because they were kind of only using colors. But LSST, you know, we were going to have, you know, a couple hundred, you know, features that we're basically, you know, trying to select from, right? So it makes a lot more sense for me to, you know, think about things in terms of the latent space. So that is, you know, you start with your 40 billion sources. You run some sort of unsupervised clustering algorithm on them. And then what your output is a lower dimensionality latent space, at least 3 dimensions. I think Matthew says 13 is needed for ZTF, right? So And then, you basically cluster your objects in that latent space, and then, you use your known objects to then label those clusters, right? So to me, like, there are sort of details of how exactly you do this, and people are working on that in various data sets, but that sort of basic construct sort of makes sense to me as the way to go for something as sophisticated as the LSST data. So I want to remind you of the data challenge paper Đorđe Savić led, and just a few quick highlights of the things from there. So I was pushing transfer learning, unsupervised autoencoders, feeding into supervised methods, like I just said. Đorđe was using variational autoencoders plus this Gaussian mixture model characterization of the latent space. So at the time, I was like, Gaussian mixture models, I didn't like that in Bovie. But now, as I've sort of played with stuff, I think it actually makes a lot of sense because he's actually applying that in the latent space, right? And I know I'm kind of bouncing around here, but these are just sort of topics I want to talk to people about. And then Weizhang Yu sort of added feature space enhancements. That's the simplest way I can sort of explain. Vincenzo and Maurizio also basically adding feature space enhancements. And these are all things that we can be working on together. I really like this approach that Paula was applying to changing states AGNs, this variational recurrent autoencoder with careful balancing of the training sample. She was applying this to changing states. I think that's the kind of thing that works well just for AGN selection in general. So I love the idea of sort of trying to apply that to a broader sample of objects. Angelika Kovacevic sent me a draft paper last week, and I just wanted to highlight some stuff from them. They're doing some really nice work with these attentive latent neural processes with mixture density models. Again, so this is doing something very powerful. The unsupervised learning drives the formation of the latent space, and then in their particular case, they're using the supervised learning to govern the supermassive black hole parameter and transfer function estimation. But honestly, I think it doesn't have to be about RM. We can apply that same kind of structure to just classification in general. Again, something for us to talk about as a group. Weizhang Yu couldn't make it today, so I wanted to highlight a few things that he has been working on. So he's done a very careful job of cross-calibrating pan stars and SDSS and ZTF. One of the nice things I think about that is the second we have one epoch of LSST data, we now have 20 years of data, right? And so you can start doing variability basically day one. And so I think that'll be really powerful. So talk to Weizhang if you're interested about that. So I'm not actually interested in RM. I am more interested in using the variability to tease out basically geometric structure that Chris was talking about, Eddington ratio, and so on. And so the basic idea here is that as your Eddington ratio changes, your geometry changes, and your variability is going to change, right? You're going to go from being dominated by the disk and variability to basically the X-ray and the imprinting on the disk and so on. And so there's things that we can learn about physics just from the variability. So I would like to not only do AGN selection, AGN photo Z, but we should basically be able to produce priors on the Eddington ratio, and all without ever taking a spectrum. So I'm going to argue in a second that X-ray binaries don't scale up to supermassive black holes, but I think that there's some really interesting things to learn from that community. So Weizhang has a nice new paper here where literally all he's done is multiply the PSD by frequency, and now the structure functions make a lot more sense. You get sort of two clear components that you can interpret, and you're getting very different light curves, right? And so here, so this is basically the same kind of thing that I was just showing, but just from a different perspective. So now we've got two components. You can interpret those two components as the disk and as the corona. So sometimes you just have the the disk component, and sometimes you have the corona and the disk and so on. And so as you trade off on these things as a function of Eddington ratio, you're going to see different variability. And again, that is going to allow us to have a prior on the Eddington ratio. And so here is just, sort of showing how those two components trade off with wavelength and Eddington ratio and black hole mass and so on. And so, just as a way for us to use the variability to tease out that information. Okay, so Wei Zhang's aiming to resubmit this second harmonic oscillator paper by the end of July. He also asked if I would advertise for his Easy Tau X paper, simultaneous variability and lag inference using multiband LSST light curves that could significantly enhance searches for electromagnetic counterparts of massive black hole binaries using LSST data. And he is also looking for his next postdoc job. He's currently at Bishop's in Canada. And like I said, just wasn't able to make it this week. Okay, so that's that. I don't think Dave is in the room, is he? Okay, so I'm going to pick on Dave a little bit, but also praise him. The new Alexander review paper. I mean, this is a really nice paper. I wouldn't have wanted to written it. You would have had to lock me in the basement for like 2 straight years and only come up for wine and cheese like once a week to read all those papers and then write this paper, right? So great respect there. But one thing I want to say is like there's at least 5 things in the first 15 pages that I just don't agree with, right? I don't think they're true. That said, they're totally reasonable things that may indeed be true, and it just might just be the color of the sky in Gordon's world that makes him think that they're not true, and that that's fine. So my point is that there are clearly open questions in the field, right? And so there's sort of 2 aspects of that, right? One is we're going to use the LSST data to try to answer those questions. But are some of those open questions like affecting how we approach things, right? How we're trying to run our experiments and so on. And I think, yes, at some level, and I just want to highlight one thing, right, is, okay, so this is the standard cartoon model of what an AGN accretion disk looks like, right? And Chris is going to scream maybe, but like, I don't think that's true. I think this is true.
I'm sure it's not.
Okay, fine. But the point I would make is the reason I think this is true is basically because of your work, right? I don't think that's true at all, right? So I would prefer not starting with Shakura-Sanayev and adding kludges to try to explain what things are doing, and taking some other model and then you add your kludges to explain, what's going on, right? So that makes a lot more sense to me, right? So Shakura-Sanayev to me is dead. Like we should just stop even talking about that. Okay, so I think I'm just gonna leave it there and let people get coffee, right? So.
Well, questions for Gordon.
Can I throw in some heresy?
Yeah.
So I don't think we will find dwarf AGN by looking for them in the ways that we're looking for them, because dwarf AGN, we're looking at low mass black holes. If they have high mass accretion rate, their disks are too hot to have a broadline region. So they won't have, and if they're too hot to have a broadline region, they're too hot to have the wind that does the reprocessing that makes us optical variability. We are not going to find them in the optical very easily at all.
Yeah, and so that's going to be a source of nuisance for the Galaxy people, because they're not going to be able to find them either, right? And so we need to make sure we're getting them.
Thanks, Gordon. The point you were making about inferring more and more physical parameters from the latent space.
Yeah.
So there's work we've been doing with Josh Fagan, a grad student, and he's put out a couple of papers where we're using these very complex latent stochastic spaces.
Yeah.
And one of the things we found is actually they're not great for inferring, even when we know ground truth and propagate it through transfer functions and all that sort of thing. They don't do a good job for a lot of the parameters. There are 1 or 2 they do, but the question is whether we've got the wrong space representation or whether we're doing something wrong or whatever, but it doesn't seem to be working as well as we thought maybe it should do in the first place.
So I guess the way I'm thinking of it is more like, the latent space for selection, and then almost a different thing, looking at the variability just to infer the physics.
So there are a number of architectures you could do. I mean, I think maybe that may be the way to do it. I mean, what Josh did was, or what we did with Ashley and Josh, was we combined into the space both it's an autoencoder space, so it does reproduce, but it also does the physical inferences of all the parameters that they put into their initial simulations to get the black hole model.
Yeah. I think my biggest concern is, okay, so for the data challenge, like everybody that submitted something got like 98%, accuracy or whatever. And it's like, okay, but the data challenge data wasn't realistic, right? It was only Joko's variable objects and so on, right? And then, I mean, I get asked to referee papers that are literally just like, here, I ran this machine learning algorithm and this is what we got, right? And I'm like, that's meaningless, right? You're just assuming that the output of your black box, right? So I think we need to do a better job of basically knowing what it is that we're getting out. Like, I mean, I have a hard time even just simulating some really simple data, running it through a variational autoencoder, and then looking at the output and basically saying, yes, I understand what this is happening. And that's only with, 30 features, right? And not, 400 features or something like that. So I think there's a lot of work that we need to do there and not just, start dumping stuff into some machine learning algorithm and treating that as like gospel, right?
Yeah. I think that's the danger.
Yeah.
Any other questions for Gordon? Okay, well, let's thank all the speakers from this first session. I believe it's now time for coffee. And do you know where coffee is? Maybe Chris will give us advice as where. Okay. How long is coffee break? I haven't checked.
Half an hour.
Okay, right. You can flip that on. Yes. And put that in your pocket.
I think, am I audible? Yes.
All right, thank you. Coming back after the break. Because we have to be out of here at a very certain specific time, I'm gonna institute something that I learned here in my first meeting at Durham in 2014. So I'll give you a 2-minute warning, and then at 30 seconds left, I'll put my hand up. And then when I put my hand down, everyone's gonna cheer for you, okay? So can we get a quick practice? Ready? All right, awesome. All right, Amit, take it away.
Good morning. I am Amit Kumar Mandal. I am a postdoctoral fellow at the Center for Theoretical Physics at the Police Academy of Sciences, where I am collaborating with Professor Bojana Charni, and my other collaborators are mentioned here, such as Vikram, Francisco, Swayam, Mohammed, and many more. Okay, so the title of my talk is Modeling Continuum Time Delays in AGNs in the LSST era, Implications for Estimating the Hubble Constant H0. Okay. Active galactic nuclei are among the most luminous objects in the universe. The typical luminosity ranges between 10 to the power 42 to 10 to the power 46 arc per second. So this is a schematic diagram of the central part of AGN, and the typical sizes of the different components in the central parts are mentioned here, where accretion, the size of the accretion disk is of the order of less than 0.001 parsec, whereas broad emission line region can extend from 0.01 to 0.1 parsec. So from these size measurements, it is clear that the central parts of the AGN are very compact. So naturally, it is difficult to probe these regions using any current imaging technique. So if there is difficulties with direct imaging technique, there is an indirect way to probe these regions, which is known as reverberation mapping or echo mapping technique. So where time resolution can be swapped for the spatial resolution. So reverberation mapping uses an intrinsic property of AGN, that is the flux variability property. So emissions at different wavelengths are coming from the different part of the AGN. So like UV continuum is coming from the accretion disk, whereas this H beta emission line is coming from the broad emission line region. So the variations in the UV continuum will be reflected in the variations in the H beta line light curves, but there will be a lag between these two light curves, which is delta t, and if we multiply the lag by the velocity of light c, that will basically give you the size of those emitting regions. So this is the basic concept of reverberation mapping, and using this reverberation mapping, specifically by finding interband time delays between different UV optical light curves, it is possible to estimate the size of the accretion disk. So here I am giving you an example of different UV optical light curves for the target NGC 5548 in this figure, and which is taken from FASTNAV 2016. And then the lag spectrum is obtained by plotting the interband time delays as a function of wavelength, and you can see that the interband time delays increases with wavelength, which is expected from standard disk model. Now, assuming using the conventional, that is the traditional method, that wavelength increases with wavelength, the interband delays increases with wavelength following a power law, which is given by this equation. So it is possible to find the accretion disk size from the normalization constant tau 0 at reference wavelength lambda 0, say at reference wavelength 2500 angstrom. So this is also known as the disk mapping, and the accretion disk size expected from the standard disk model is given by this equation. So then we, at wavelength lambda, then we compared the observed disk size obtained from disk mapping with the expected disk size from the standard disk model in this figure, where the y-axis represents the observed disk size from disk mapping and the x-axis is the expected from standard disk model. And you can see that there is a systematic offset between these two measurements, and we found that the observed disk size is found to be about 3 to 6 times larger than the expected disk size from standard disk model. Also from microlensing study of gravitationally lensed quasars, this kind of discrepancies is observed, about 4 times larger disk size is found. So this is also known as the disk size anomalies. So now it is believed that contamination from outer region like from the BLR is mainly responsible for such kind of disk size anomalies. So our objective is to fit each point in the lag spectrum individually, that is separately, not by assuming a power loss dependency, but we will fit each point separately in the lag spectrum considering disk emission as well as BLR contamination. So to do that, we first assumed a lamppost standard disk model plus lamppost model. So according to the lamppost model, a point-like source is producing X-ray radiation, which is illuminating the accretion disk at radius r, and the flux at radius r is given by this equation, and from this flux we can estimate the temperature which is given by this equation, and once we know the temperature at radius r, we can estimate the disk transfer function from the Planck function by using this equation. So then we estimated the disk transfer function for NGC 5548 by using the parameters which are summarized here, and we estimated this disk response function for different values of lambda wavelength, which are shown in this figure. And from this figure you can see that the disk response functions are originating from a single point which corresponds to the inner radius of the accretion disk, which has very high temperature. That's why it is producing radiation at all wavelengths. And also the disk response functions are found to become broadened as wavelength increases because time delays increases with wavelength. But the time delays obtained from this disk response function are found to be smaller than the observed time delays. Now to fit the observed time delays, then we included contribution from outer region like from the BLR, because the continuum from the disk travels through the BLR where it encounters scattering as well as reprocessing, and because of those an extra time delay is introduced before reaching to the observer. So to estimate this contamination from BLR, so we need to know the BLR response function. And to know the BLR response function, we need to know the BLR cloud positions. And to get the BLR cloud positions, we need a BLR dynamical model. So for that, we are using FRADO model, our FRADO model, that is Field Relatively Accelerated Dusty Outflow model. So this model is also developed by our group. And so using this model, we are basically estimating the cloud positions, and from that cloud positions we are estimating the BLR transfer function, and also this BLR response should be modulated by the emissivity profile of the BLR, which is computed using cloudy. Then the total transfer function is obtained by using this equation where the disk response function, the BLR response function which is modulated by the emissivity profile is also included in this total transfer function. And BLR is the BLR fraction which is contributing to the continuum delays. So now I am showing an example of this model. So here in the left panels, the top figure represents the disk response function, the middle figure represents the BLR response function, and the bottom panel represents the BLR emissivity profile. Then we merge this using this equation, we obtain the total transfer function. So you can see that the total transfer function shows two peaks. One peak arising at smaller time delays is mainly because of the disk response function, and another peak arising at the larger time delays is mainly because of the BLR contribution. And then we estimated the time delays at different wavelength using this equation, And then we compared our model recovered time delays with the observed time delays in the lag spectrum. So here in the lag spectrum, the black points with error bars represent the observed time delays as a function of wavelength. The red circular points represent the time delays obtained from the disk response function only, which is smaller than the observed time delays. And the brown points represent the model recovered time delays. So you can see that the model successfully recovers the observed time delays almost. So now the advantage of this model is that this model, specifically the Prado, is independent of luminosity distance. So so we can use this kind of model to estimate Hubble constant. So now the next step is to find the Hubble constant. Okay, so to estimate the Hubble constant, we simultaneously fitted the lag spectrum as well as the spectral energy distribution for NGC 5548. And we fitted these two spectra for different values of luminosity distance, and the best fit parameter is obtained from chi-square minimization technique. And here in the right panel, so the top figure represents the chi-square values in the luminosity distance space, whereas the bottom panel represents the chi-square value in the Hubble constant space. And for best fitting, we found that the luminosity distance is 62 megaparsec for NGC 5548, and from this luminosity distance, we found the Hubble constant to be 79.8 kilometers per second per megaparsec, with an error of 10 to 15 kilometers per second per megaparsec. So this value is almost consistent with the value expected from standard lambda CDM model, but still we are facing large errors. So now to reduce the error and to address the Hubble tension, we started a new AGN monitoring project for a large sample of AGN. So we call this project as HALO, Hubble constant constraints through AGN light curve observations. So we initiated this project in 2024 using 60 centimeter Observatory Supermassive telescope, which is situated in Chile. And we have 150 AGNs spanning over a range of redshifts. And for photometric monitoring, we are using filters, specifically we are using Stromgen filters, US, VS, VS, YS, and one Johnson-Cousin filter IC. And we have chosen these filters in such a way that we try to avoid any prominent broad emission line features within the filter band process to minimize the contamination from the BLR. So this level of precision in filter selection was not adopted in previous photometric container reevaluation mapping RM campaign. So here I am showing you an example of the filter transfer curves, which are overplotted on the spectrum of Carroll 9. So as part of this HALO project, so we completed observation for one object Carroll 9, and we are still observing the two targets, NGC 3783 and WPS48. So for Carroll 9, I am showing you the light curves in U, V, B, Y, and I filter in the left panel, and the typical cadence is less than 0.5 days for Carroll 9. And for NGC 3783, this is a low luminosity, relatively low luminosity AGN, and the typical cadence for this AGN, this light curve, is about 20 minutes. And WPS48, this is a relatively high luminosity AGN, and that's why the typical cadence for this target is about 1 day. We are still observing these targets. And okay, these are, so the observation is completed for Carroll 9, and we are analyzing the data now. We will also apply our model to this to Carroll 9. Okay. Okay, using traditional method, it is also possible to perform disk mapping and to constrain the disk size, like assuming a parallel dependence of interband delays on wavelength using this equation. So we perform this disk mapping on several AGNs, specifically using light curves data from Seoul National University AGN Monitoring Project, SAMP. And then also we integrated measurements from the literature, and using those measurements together with the measurements from SAMP, we constrain the disk size luminosity relation, and which is shown in this figure, and you can see that they are strongly correlated, and this relationship is equivalent to BLR size luminosity relationship. That's why then we check the correlation between the BLR size and the disk size, and we found they are strongly correlated, and BLR size is found to be about 17 times larger than the disk size at 2500 angstrom. And this BLR size disk size relationship is very important because this relationship can be used to estimate black hole mass from a single epoch spectrum. So for that we compared the black hole mass obtained from the disk mapping, that is from photometric ray aversion mapping, with the black hole mass calculated from spectroscopic age beta ray aversion mapping, and which is shown here, this comparison, and you can see that we found negligible offset with intrinsic scatter of 0.3 dex. So this photometric ray aversion mapping can be used to estimate black hole mass, and the advantage is performing photometric ray aversion mapping is much easier compared to spectroscopic ray aversion mapping, both in terms of getting time and cost. Okay, so here I summarized what can be done with LSST data. So LSST is going to provide light curve data in 6 filters, that is UG, RI, ZY filters, and we can apply our newly developed model to constrain the Hubble constant specifically for the deep drilling field, and which is expected to provide a few thousands of sources, and the additional requirement is the spectral energy distribution. And future LSST data will complement our HALO project, which significantly expand the lag spectral wavelength coverage for a few selected AGNs, and assuming the traditional method, that is the parallel dependence of interval delays on wavelength, it is possible to use photometric light curves from LSST data to constrain the disk size luminosity as well as the BLR size disk size relations over a large dynamic range in the luminosity, specifically for the high luminosity AGNs, which basically offer a cost-effective method for estimating black hole mass. Thank you.
Time for a quick question.
So my apologies if I missed this, but for your continuum reverberation mapped objects, what is your best estimate of the level of contribution from diffuse BLR continuum and BLR lines versus true disk variability?
About 20% BLR contamination.
20%, okay.
20 to 30%.
Right. And so, you know, there have been other people, Hagai Netzer perhaps most famously has been claiming it's actually dominated by that. What is your assessment there? Have you compared with his thinking?
Yes, if you see the recent studies by Edelson 2024, so they have performed this mapping on Fair Online recently. Yeah. And they also try to use higher nature model, and they did not able to feed the data if we consider only BLR contribution. So there should be some contribution from, that must be contribution from accretion disk. So BLR so we have to consider accretion disk contribution as well as BLR contribution. And yes, the delays can't be explained only in terms of BLR diffuse continuum.
20%.
Yes.
Okay.
If you have the quickest question.
Doesn't that depend on the timescale on which you're looking? If you're looking at the large lag times, then it's dominated by the borderline region. If you're looking at the short ones, it's dominated by the accretion disk.
Yes. Okay, very good question. And that's why some people try to detrend the light curve. I don't like this detrending personally. Okay, so the idea is to remove the slower variations in the light curve as using this detrending, so which is basically because of from larger regions which are coming contribution. So so we experimented with detrending, without detrending, and we found that this kind of detrending there is no standard way to perform this detrending to remove these slower variations, and it is varying a lot. So I don't know exactly the reason, but if you are talking about this higher time scale variability, something like that, so that is actually coming from outer region. So, but if you are considering only original light curves, so and also the advantage of our model is as we are considering both the disk and contribution from outer region, so there is no need to perform any kind of detrending, any kind of artificial implementation on the light curve. Mm-hmm.
All right, let's thank him again. Hello, hello. Maybe I just hold it. It's better. Take it away, Shana.
Okay. So hello everyone. My name is Shanita. I'm postdoc working at the University of Southampton with Panda. And today I would like to present our results of the some preliminary results of our measurement of host galaxy properties of quasars by 2D image decomposition. So yeah, and this is basically an application of the near-infrared data fusion pipelines that Elham and Raphael has developed. And by the way, so the background image is the ChatGPT view of Durham Cathedral with black hole. Okay, so I don't think I really have to convince this audience that the host galaxies of agents are important, but let me still try to do it in one slide. So from the studies of local galaxies, we have learned that there's a tight correlation between the black hole masses and the bulge mass of their host galaxies with the intrinsic scatter of only 0.3x. However, to understand what kind of role that agent plays in galaxy evolution and also cosmic evolution, we need to understand whether this means a co-evolution between supermassive black holes and host galaxies, or if it's not. Or if there's a co-evolution, how does it happen? So basically, there are two approaches to understand this kind of correlation. The first approach is we think there's a physical cause of this correlation, which originates from the agent feedback and self-regulated black hole growth. So the black hole properties are kind of correlated with ISM and CGM properties, and in some kind of complicated physical processes. And also, there's another approach if we think there's no physical cause of this scaling relation, but it's actually just a trick of statistics, as suggested by this Young and Mathieu 2011 paper. So even if you start with some black hole seeds and galaxy seeds with any random distribution and under a hierarchical growth scenario, so if two galaxies and two black holes merge with each other, you just simply sum up their masses, you eventually end up with some scaling relations. And you don't need any agent feedback in it. It's just a statistics. And it's called the central limit theorem. So no matter which scenario do you prefer, which one do you want to test, we need the information of the host galaxies. In this case, we need to know how do black holes interact with their ISM, their host galaxies, via the feedback effects. And in this case, we have to check, well, whether the merger ratio is enough to form this tight correlated scaling relation over cosmic time. So, so the best option to study the host galaxies of agents is, of course, using the space-based telescopes. And the frontier now is you can use JWST to reveal the quasar-host galaxies at redshift 6. And this is a recent paper by Xu Ding et al. 2025, and in which they studied the host galaxy of 12 quasars at redshift 6. And the first row is the data from JWST-NIR. And second row, they use the tool called Galactic, which is Galaxy Shapes of Light, which I'm also included as a co-developer of this tool to remove the point source from the image. And for some of the cases, you can reveal the host galaxy of these redshift 6 quasars. However, well, JWST is revolutionary in resolving quasar host galaxies, but the sample size is very limited. We still don't understand very well about the general host galaxy properties of the entire agent population. So the problem is how well we can do with ground-based imaging, like with LSST, where we have much better statistics. Okay, So here I have two sets of images for 4 SDSS quasars at redshift of 0.73, 0.64, 1.1, and 1.44. So I want to ask for a vote from the audience. How many of you think that the first row, so one of them is from LSST, and one of them is from Legacy Survey. So how many of you think the first row is from Legacy Survey? No? And how many of you think it's from LSST? Okay, that's good to know. Okay, so obviously LSST is doing a better job. So the first row is from the LSST first light data released on June 23rd. And second row is from a Legacy Survey. So you can see with LSST, we can resolve more about the faint emission of the galaxies. For example, the spiral arms, extended emission of the host galaxy, and also potential secondary sources or the sources in the environment around the quasar. So this gives us a potential power of LSST to reveal quasar host galaxies, maybe up to redshift 1 point something. But the main challenge is not only the faint emission, but also the contrast between the quasars and the galaxies, because the quasars usually overshine the host galaxies. So that's why we need to use the 2D image analysis tool to remove the quasar, then to study the host galaxies. Okay, so thanks to the work of Elham and Raphael, so the development of the VISTA IR fusion pipeline has been run for the XM and LSS field. And from this field has overlap with DES year 3 catalog. And in this catalog, there's a dwarf agent samples from Collingbook et al. 2022 paper in which they have 172 variability selected agents in the SNX3 field. And within these variability selected agents, there are 78 sources with SPEC-Z measurements and 37 sources at redshift between 0 and 1.0. And for this set of sources, we did a preliminary test of image decomposition and 2D image analysis of all these 8 bands of data from HSC to VISTA. So these are the decomposition results for example of redshift 0.61 agent on HSC GRIZY and VISTA JHKS bands decomposition. So for each row, the leftmost panel is original data, and the second panel is the best fit model with PSF plus 30 profiles, and the third panel is the host galaxy image after you remove the point source from the data, and the fourth panel is a normalized residual. And also the analysis of this decomposition is done on LSST-RSP, and I also want to emphasize that the VISTA images and the catalogs are available on UKRSP via data.butler. So previous works have also done similar things on HSC images, but we've extended the usage to the near-infrared VISTA images as well. Okay, so after doing that, what we do is to measure the stellar mass with SED fitting using SIGAL. So we did it in 2 different ways. So in the left panel, we don't apply any image analysis, but just do the SED fitting on the photometry. So you have an agent template in the SED fitting models. While for the right-hand side panel, we first apply the image decomposition. So we apply the SED fitting only on the host galaxy image. So we don't need agent template in this case for SED fitting. So if you compare the stellar spectrum, the stellar SED that you get from the photometry level decomposition, which is a yellow curve here, and the black curve that we get, they are, almost consistent with each other, which is a good signal. And also if we compare the stellar mass measurement from these 2 different methods, so the x-axis is if we only use SIGAL and doing the decomposition at the photometry level, and the y-axis is if we apply the image decomposition first and then the SED fitting. So they basically follow a 1-to-1 relation. However, as you can see, the uncertainty range of the SED decomposition with photometry is much larger on the horizontal axis than the vertical axis if we apply the image decomposition. So how does it change? So like the median stellar mass uncertainties would be around 72% for the decomposition in photometry level, and that reduces to 18% if we apply the decomposition of image first. So that is good. We're happy. And however, for the SFR, for the star formation rate, the median uncertainties was 134%, and that reduces to 73%. So it's still not very good. So our kind of view here is that the image decomposition can significantly reduce the uncertainties of stellar mass measurements, but the SFR stays difficult. Also, people have to think about the computational cost of you doing the image decomposition and decide kind of the balance between the uncertainty level you want and the computational power. And also from here, you can see the reason why we want to include the VISTA bands, because the contrast between the stellar emission, which is the orange curve here, and the agent emission, which is curved down here, is higher in the near-infrared bands. So you have more chance to see the agent host galaxy in those GHK bands. Okay, so I would like to give another comparison on if you include the VISTA band and don't include the VISTA band, what is the difference? So the left-hand side, we don't have the VISTA band data, and the right-hand side, we include the VISTA band data. And this is comparison between the stellar mass of these two cases. And we see if we use only the HSE photometry for SED fitting, that leads to a plus 0.2 dex offset in stellar mass at above 10 to the 10.1 solar mass, compared to using both HSE and VISTA data. And this offset is actually large. As I mentioned in the introduction slide, that the intrinsic scatter of the scaling relation is only 0.3 dex. And the reason of this kind of overestimating, if you only use optical bands, is probably because the massive galaxies are dominated by older stellar population, which are better captured in the near-infrared bands. So the point here is that VISTA photometry helps to constrain the SED shape at high stellar mass end. Okay, so this is results where we put the black hole mass versus stellar mass stellar mass results for all the samples, all the 37 agents in SN-X3 field, and compared to the local scaling relation. And this is a work, original work done by Collingburg et al. 2022 for 23 agents in these three fields. And basically, we are finding similar results that the black holes of these variability selected agents are still overmassive compared to the local scaling relation. But of course, we have to consider the selection bias because, well, brighter agents are easier to be found as variability selected agents. And that needs a better understanding of the selection function. So I was suggesting is, well, early LSST results, still rely on, I think it will still rely on the SDSS and other quasar catalogs. And because I think the variability selection will take time to do. And the main improvement that we've done is from the DCAM to HSC and to LSST and beta image quality, and including the image decomposition will reduce the degeneracy of SED fitting. Okay, so because I still have a bit of more time, I would like to talk about some more things we can do with this image analysis. It's not only the measurement of the stellar mass. So when we ask, how can we characterize the galaxy? Maybe people will think about, well, the size, stellar mass, star formation rate, metallicity, extinction. But all of these things, we call them as parametric properties of galaxies. Compared to that, we have another way to characterize galaxy, which calls them non-parametric. So the difference is all these properties are based on some models that we already know. So we fit in the SED models or some luminosity mass relations, or it's based on something we know. But these non-parametric properties are just based on the pixel levels. So how was these things defined? For example, the asymmetry value is defined if you rotate a galaxy by 180 degrees and subtract it from its original image, you get a residual image. And if you normalize it with the original flux, you get a symmetry value between 0 and 1. If it's larger, which means your galaxy is more asymmetric. And for the smoothness value, if you smooth the galaxy image by a Gaussian filter, so basically blur it and subtract it from the original image, so you'll get how smooth your galaxy is. And then the concentration as well, how much light is concentrated at the center. Thank you. So as you can see that these parameters describe the galaxy morphology in a model-independent way. And of course, this method heavily depends on the point source subtraction method. As you can imagine, if you have a point source at center, very bright point source at center, then the source must be symmetric. And it must be, well, smooth and also highly concentrated. But that doesn't make any sense because what we are interested in is aging host galaxy. So that's why we can also implement this measurement in our pipeline of 2D image analysis. So, but why is this thing interesting? Why do we bother about the asymmetry? So the answer is, if a galaxy is under steady growth, it's dominated by self-gravity, then it will develop even axial asymmetry. So what does it mean is if you rotate a galaxy by 180 degree or 90 degree, you'll find some similarities in the image. And actually, one of the Consulate paper have shown that the high asymmetric galaxies are usually associated with short time scale randomness, for example, starburst and and supernovae, and also external effect, for example, galaxy mergers. So as you might have noticed that these kind of events are associated with star formation. As I've mentioned, the star formation rate is difficult to measure with SCD fitting, even with image decomposition. However, the asymmetry value could be an alternative way to probe the specific star formation rate. This is the results from Salvato 2021. Of course, the specific star formation rate has a correlation with the stellar mass. However, what is also important is vertical to this relation. What decides the scatter of the star formation rate at the same stellar mass? It turns out the asymmetry value could be a good probe. So the bright colors refer to higher asymmetry values. So more asymmetric values tends to have higher specific star formation rate at the same stellar mass of a galaxy. Okay. So I think because I'm running out of time, I might skip this, do this very quickly. Okay.
Yeah, we have 30 seconds.
Seconds. Okay, let me just quickly say this. So the Jana et al., this paper about the mergers, it's oversimplified model because you don't know whether the galaxies, how the galaxies and black holes grows via the mergers. And you need like the detailed equation or star formation rate properties of these samples. And what we can do is search for dual quasars. We have access to both the black hole properties and the host galaxy properties for both of the sources. And we are doing a test in the XMM source field from the Penn State group and to search for this kind of spatial sources, and which can also be done with the image analysis technique, which I can talk in more details if you are interested later. And finally, I leave my conclusion slide as a big picture that we are working on the 2D image analysis pipeline on ISP to analyze host galaxy properties of low-Z AGNs with currently HSC data and the VISTA data, and we will produce image products and catalog products, including all these parameters for scientific research. Okay, thank you.
We have time for a quick question.
So in your Segal-based fitting, which looks very good, have you included the X-ray data or detections or upper limits as a prior? That can be very useful for breaking degeneracies.
No, we haven't applied the X-ray data for this sample set because not all of them are detected in X-ray.
Yeah, so you can use upper limits then. Yeah.
Oh, yeah.
Yang et al. Have built in X-ray functionality into that, which could be quite helpful for your work.
Thank you. I'll do that. Thanks.
All right, if there's any other questions, we can continue during lunch. Let's thank Shenli again. And our next talk is remote.
Hello, do you hear me?
Yes.
Hi, everyone. I guess I can share my screen. Do you hear me well? So,
yes.
Do you see the slides and everything?
Yes.
Okay, great.
Good to go? Okay. Yeah, Dragner, good to go.
Okay. Thank you very much. I'm happy that to be able to present this work of our task force in the first day of the meeting. So thank you very much for the organizers. And I apologize for not being there in person. This week, we also have a summer school for master students, and I have to be here in presence. So this is a talk dedicated to the current and future follow-up campaigns of close binary supermassive black hole system, and with the focus of those which will be discovered with the LSST. And I present this on behalf of my co-chairs, Marta Fatovic and Andrzej Kovacevic. Marta is also there in presence, and I hope you will have a chance to discuss all of the activities that I'm going to present here with Marta, and especially at the last day discussion sessions when different follow-up watch list will be discussed. So the previous speaker, we were mentioning the dual AGNs, and we all know, and I don't have to convince you, that galaxy grow through mergers, and that as a final stage of the merger, we should have a binary supermassive black hole, and also at the last stage, we should have the closer binary supermassive black holes. And why these are very important for us, because these compact supermassive black hole binaries are basically targets for new generation gravitational wave telescopes. And one of the aims of this group of people is basically to produce a catalog, an LSST catalog of the primary targets for the next generation gravitational wave telescopes. And the biggest question is how to find them, which we are all working on this. And for now, we basically have the candidates of these compact supermassive binary supermassive black hole binaries, and you can find several in these references. So, what are the prospects for the LSST? So, what are the probability and the density of detection of the binary supermassive black hole? It basically depends a lot on the configuration of the system in terms of what are the masses of the components and what are their separation and what are the periods basically. And we talk here about let's say millions of possible candidates that LSST is going to detect in terms of binary supermassive black hole. But we also estimate that there are going to be a dozen of very ultra compact binaries, which are with a period of less than 1 day. And I refer to you to check the recent the previous work of Xin and Hyman, and also the recent one, which is just about to be published. So and of course there is a lot of also discussion in terms of how much we can basically optimize the depth and the time coverage of the LSST in order to do the better periodicity data mining in terms of the binary, in terms of observed quasars. So we are definitely going to detect the candidates, but in order to confirm them, we need to we need to organize the follow-up observations, and there is a large subgroup within the AGN Science Collaboration, which is dedicated to follow-ups, led by Claudio Ricci and Bin Dorani. And the main tasks of this group is to identify methods to select first of all the most interesting sources, the so-called golden samples, and also to identify facilities and resources. And there are several let's say task forces within this follow-up subgroup, and I'm going to focus on the binaries. And I'm also going to mention a little bit about blazars, as I was kindly asked by the co-chairs of this task force that are not present in person to mention and to advertise their activities. So the binary follow-up task force is chaired by the co-authors of this presentation, and you can follow all of the activities on the Slack channel, dedicated Slack channel within the LSST Discovery Alliance. And the task force of these actions are basically to work on the identification of the best candidates and the selection for the follow-up, defining basically the selection criteria. And here I have to mention the key word, and this is going to be repeated a lot, that we are all the time working in synergy with all the other teams. So of course the data management and Rubin Science Platform team and alert brokers, as well as other task forces within the AGN, such as the binary supermassive black hole task force, the AGN watch list task force, and so on. So some of the activities of this task force, ongoing activities, and we have basically started to work beginning of this year. We have submitted a joint proposal with other LSST science collaboration led by basically desk team. So there were two long-term proposals being submitted, one for the Gemini long-term program and the SOAR telescope. And one of it, the SOAR telescope application, has been just approved a few weeks ago. The other important task that we are working on is the selection of candidates, and here our aim is to basically to compile the list of all possible candidates. And here I'm just showing one table produced by Donna Razio and Maria Carisi from their paper from 2023. So there is a list of several hundreds of binary candidates from their paper with all the details, and this is all available on our dedicated drive, which is can be found at our the links can be found at the Slack channel. We also organize expert talks, and one talk was just given by Cheng Xin about the identification of the compact supermassive binaries using the LSST and the follow-up of their research on number density of the candidates that will be discovered by the LSST. Finally, in the second part of the talk, I want to present basically a case study and how basically our activities of our follow-up group are going to be organized. So, and this is the case study of one SDSS quasar, which is a closed binary. A candidate for a closed binary supermassive black hole system with a period less than 1 year, which is a candidate very, let's say a good candidate for the watch list and the follow-up with the LSST. So the one thing, and this is something that we are going to again do for LSST, is the survey data mining. So in the case of this object, it was discovered once we were basically did the data mining of the SDSS STRAP 82 catalog, and this was work led by Marta Fatovic, who was searching for periodic objects from the standard catalogs. And out of 1 million light curves available in the SDSS STRAP 82, 5 candidates were selected to be periodic, and all of these were actually had a quasar archival spectra. What was important to say is that for the analysis of the periodic oscillation, we employed several tools. So apart from a multiband Lomskargo, which is going to be a standard in the Rubin Science Platform and the standard run by the data management team, we also combined this with with the domain, with the time domain periodic variability mining pipeline, the QHX, which is a software offered by our Serbian in-kind team led by Anđelka Kovačević. And both technique confirmed that this candidate has a period of around 800 days, and the average magnitude was 21.5. Why am I mentioning that this magnitude is that you need a large telescope to do the spectroscopic follow-up. So here are the light curves. I'm just showing here the folded light curves in different filters. And here, this is only as to the left, you can see only SDSS data, and to the right, it's combined with the Penn stars and the ZTF. And fortunately, in just a few months, we will add here also the LSST data. So what is important is that we need to combine the many techniques for the periodic, for the search of a periodic oscillation in order to avoid false positives. So since this object was not bright enough for a small size telescope, we needed to apply for large programs. So we observed it with the follow-up to get the high signal to noise ratio spectroscopy with the Gemini South and the Magellan. We obtained 2 epochs, and here you can see the archival SDSS spectra, which motivated us to continue to do the follow-up, since you see the broad and very broad Magellan magnesium to line profile. So when compared, these are these three spectra from 3 epochs compared with the SDSS, Gemini, and Magellan, and you can see a significant change in the line profile in terms of the width and the position of the peaks, and the second peak appearing. So what we modeled this with our binary supermassive black hole model, which you can find the details in these 2 publications, Popović et al. And Simić et al. 21 and 22. And we modeled this with the system of 2 supermassive black hole with a large mass ratio, where the smaller component is less massive. The less massive component actually has the broadline region, and it's orbiting the more massive component, which does not have the broadline region. And we also have the circumbinary region. And these, you can see here the model in 2 phases, which was able to reconstruct the observed line profiles. Of course, we need more data for the final conclusions, and we are very much looking forward to the LSST bands. Actually, now not maybe for this object because it's more to the north, but for these and other candidates, we also have several candidates from our search. But we need more observations to show and confirm the periodic change in double peak, which is coordinated with the photometric periodic variability. And we have now 2 other epochs with Gemini, and which are showing again dramatic change in the line profile. And we have applied for X-shooter and for LBT observations as well. So these are preliminary findings. Stay tuned. More analysis is just to come, and these are the latest observations. And we are working on the next publications. So I'm going to use, I hope I have just a few more minutes, and I just want to do a few announcements and presentation of the Blazers follow-up task force, which is coordinated by Claudia Reitieri and Filippo D'Amando and Yannis Liodakis, who are aiming to select Blazer candidates based on their optical variability and colors, together with the multivalent behavior, which is of course very important for especially for Blazers. And their aim is to study their variability on statistical grounds, of course, with the LSST, and to investigate Blazer environment to recognize their parent population. And some of the sources of particular interest for this task force are, of course, the neutrino candidates, so multi-messenger objects, search for these quasi-periodic sources with robust period estimates like the P287 or PG1553, and many others from the literature. Some strongly lensed blazars and blazars whose outbursts can be due to microlensing by stars in foreground galaxies and so on. So if you're, I was kindly asked by the co-chairs of this task force to join their monthly telecons and to follow all the activities at Discovery Alliance Select. We all have a similar name, so it's always AGN, Science Collaboration Follow-up, so blazars, binaries, and so on. And to summarize, here is again the summary of all the activities and the objectives of the follow-up binary task force. And thank you very much for your attention.
Time for questions.
Hi, Dragana. This is Maria.
Hi, Maria.
So we may have discussed this in the calls, but I'm wondering if there is a concrete plan to develop a protocol of which candidates we follow up and with what facilities, how much time we spend on each, what wavelengths, and so on. And if we are doing that, what is the timeline to, have this protocol in place?
Yeah, this is absolutely the most important question that we as a follow-up subgroup, including other task forces, should define. Absolutely, we should have a protocol. I mean, it would be helpful, first of all, to identify this as Claudia is referring to the golden sample, and then define the procedures. So, for example, we already have within this. We should identify the sample and then the key facilities, which are either obtained through the proposals, like long-term proposals and the target of opportunities, or with some, let's say, I haven't even discussed this, with some dedicated time at certain facilities. So I invite you there in person to discuss this together with Marta and provide during the coffee breaks feedback. And I invite you all to join us on our next monthly telecon, which is going to be like late August, early September. So thank you.
Time for one more question.
I'm very happy to see the full room. Hi to all the friends, and I'm very sorry that I'm not there in person. And I'm very happy to see you all, even on Zoom. And I thank the organizer for providing the video of the audience. That's very helpful.
All right, let's thank Dragana again.
Has been asking something online, I think. But I don't know if it's
maybe, yeah, okay.
Okay, we can read it.
Maybe we can put that on the Slack as well.
Okay. So, Jana, can you please stop sharing so I can share?
Am I sharing? I don't.
Yes.
Wait, I am a bit lost now, and that's why yes, sorry. Oh, gosh. Oh yeah, my screen. Sorry. Now I see
It's
it.
fine. Thank you.
Oh my gosh. Is it okay now? Did I stop sharing?
No.
Because to me it says share. Then I have to share. Okay, let me share and then stop.
Okay,
sharing.
now you stopped.
Okay, sorry. Thank you very much.
No, it's fine. Don't worry. Oh.
Okay. Next we have Demetra.
Okay, so hello everyone.
Thanks for the chance to present this work, and it's very nice to see you all again. So I assume that this thing doesn't work. Wait. Okay, I assume and I hope that most of you have at least heard about this series of works that are focused on two of the deep drilling fields, the Cosmos field and the Chandrari field south, and that are led by our group. Have been led by our group in Napoli. And, we focused on finding AGN via optical variability. At the beginning, we adopted a more traditional approach. At some point, we switched to machine learning. There are also some works that characterize our sources, investigate their structure function, their properties. Okay, and I guess you also know, but most of you also know why we chose to use this data set, the VST data set, especially for Cosmos, for this kind of analysis. And this is because it can be seen like a very scaled down version of what we will have from the LSST survey of the deep drilling fields. So specifically, you see the covered area is 1/10 of what we will have for a deep drilling field. The baseline is for Cosmos roughly the same that we have for we will have from the LSST. And so not only they are comparable, but also you could think of merging them, combining them, and double the length of the light curve. The sampling for us is highly regular, so I wouldn't go there. Okay, originally it was a 3-day cadence, but then the data set is not as regular as we wanted it to be. The single visit depth is generally comparable to that of the LSST. I didn't report the other bands that we use here. Sorry, I just forgot, but they are roughly consistent. And you see, we use half the filters that would be available with the LSST. So our basic idea was to provide some low performance expectation, okay, some lower limit expectation for what we will have. And in the work I'm presenting today, that was published a couple of months ago, we used for the first time two bands, not only the R band, which we have been using extensively, but also the G band. Now, the first thing is that these bands have a different cadence. As I mentioned, cadence is highly irregular. So we had 54 visits in the R band and 25 visits in the G band. Now, the idea was to compute features from both bands, okay, because we want to use a machine learning approach, and specifically a random forest algorithm. And so we want to compute features, but in order to do so, if we want to compare them properly for the same source, we need to have the same number of points, of course, in a light curve. And so the first thing we did was resort to data imputation. So basically, you see this table here. There's our data set. Where you see these light or dark yellow areas, it's where we could use that imputation, meaning that we replaced gaps that we have in one band, for example, here, and not in the other, by means of linear interpolation. Now, this is something you cannot always do, of course, because you don't know how an AGN is going to vary. But we set a threshold of 15 days, and we assume that within such a short time scale, the optical variability, that is what we are interested in, should not deviate significantly for most of the sources, for almost all of them, from a linear behavior. And so based on that, we end up with 33 contemporary observations in the two bands with the same number of points. So our label set is highly unbalanced because we have roughly 2,000 non-AGN that can be either stars or inactive galaxies. Now, we selected them from different catalogs from the literature and also using different diagnostics to validate their nature. But the classifier we're using is binary. I'm just saying for the sake of completeness that we have two different types of sources in the non-AGN class. While the AGN that we are using, you see, are roughly 400. So this is a smaller sample. And they consist of sources that were classified spectroscopically as type 1 or type 2. And this classification comes from the Chandra Cosmos catalog. So we're talking about sources that were classified in the X-rays, that were observed in the X-rays, and then there are their optical spectra classifying them as type 1 or type 2. And then there is this non-overlapping sample of sources that were selected based on the mid-infrared criterion proposed by Don et al. In 2012. And so, and these sources do not have a spectroscopic classification. I should mention that there are in here, among the spectroscopic sample, some sources that also have this property in the mid-infrared. Okay, what is not in this label set for now are the sources that are classified only on the basis of their X-ray properties. Now, this is because we wanted to compare this work to the one we published in 2021, and so we wanted to use the same label set. Then we added these sources in the subsequent work. You'll see that. The features that we use for for AGN selection? Well, partly were the same that we used in the past. So the classic features, the clubbing variability, the features that are used for time series analysis and are in the FATS library in Python, a morphology indicator that comes from the Cosmos ACS catalog, and the five colors that we can obtain from the LSST bands. And there is also one mid-infrared color, this one that is obtained from Spitzer, and if we wanted to reproduce this work over LSST data, this one might be an issue. I mean, reaching Spitzer's depth might be an issue if we consider more extended areas in the sky. Okay, we don't always have the coverage. We would have WISE, but of course that would be shallower. And also we included a set of bivariate features, meaning that we combined the two bands. Now this is a long list, and I didn't include it, but also, spoiler, they turned out not to be very important, very relevant. Okay, so I will skip this part about the bivariate features, but if you're interested, I can tell about them. There's a paper on that. Okay. So basically, we tested different random forest classifiers with using different bands, combining the two bands together. Okay, and so also different features. Here are the hyperparameters that we focused on, because in order to optimize the model, you choose the best values for these hyperparameters. Of course, you cannot test the potentially infinite combinations. So this is what we use, and these are if you're interested, these are the details, okay, about the classification. Basically, what matters now is that we tested, first of all, the R band with all the original points, so the higher cadence, then the R and the G bands with the visits obtained from this imputation. Okay, then we combine them together and so on. And we also combine them as a subtraction of magnitudes or features. Okay, what I could tell from this, what we could tell is that basically there is not a single model that performs strikingly better than the others, but maybe we could tell that the first one, where we have a higher cadence, has a slightly better metrics, which is telling something that we already proved in the past, and we know, meaning that the number of visits matters. So once again, we see that if we have the chance to include more visits, we should definitely do that, because it improves things, even if it's not dramatic here. Okay. Then we need another test. So we started from 33 real visits, okay, in the R band, and then we progressively replaced 4 of them, 4 by 4, by synthetic visits, because we wanted to verify if adding synthetic values to our light curves had an impact, a significant impact. And you see the results are here in this table. If you have a quick look at the various columns, you don't see anything really dramatic, okay, in these metrics. And then that's what I think is the most interesting part of this work, because people who know us as a group know we've been struggling to find obscure AGILE via optical variability. This is generally our pain, And so we also know that we do observe it. So we wanted to try and optimize the selection. So we compared the distributions for each feature for the subclass of obscure AGILE and non-active galaxies. Why? Because typically these two are the hardest to disentangle. So we used a Kolmogorov-Smirnov test to see which features were most relevant, were better in separating the two classes. And here is the list of the features that we identified. And so what we did at this point was iterative. So we went through all the hyperparameter optimization procedure. We classified our sources, okay? And I should mention that every time we did 10 independent experiments, and so that's why in a table you see an average value and an error bar, because it's from 10 independent experiments that you get it. Then we have a feature ranking. We get rid of the least important feature. We go through it all over again. So again, hyperparameter optimization, classification, feature ranking, and so on. And we stopped when we realized that a further reduction in the number of features didn't significantly or at all improve things. That is, we stopped here. Now you see that there are half the features are colors here, but there's also the morphology indicator, and there are also variability features that turn out to be very important. And this model, the one corresponding to 8 features, which seem to be the best one in terms of selection of obscure AGN, returns a 68.1% fraction of obscure AGN. Now, as a comparison, in our previous work from 2021, we found 36% in the best case scenario. So we are almost doubling this number. Of course, this is something that comes at the expense of contamination. Okay, so we need to check, especially the true negative ratio here, because if it drops by 1%, it's dropping by 20 sources. And we have a very small label set. So imagine what would happen with a much larger data set. Of course, this is something to keep in mind. And now I just wanted to mention briefly a paper that is about to be submitted hopefully by the end of next week. Okay, where basically we use the G, R, and I bands together for the first time. So we use 3 of them, but we do something a bit different. So we select independently in each band a sample of AGN candidates, so we don't need the light curves to have the same length in this case. And we also added the sources that were confirmed as AGN just on the basis of their X-ray properties. So we test 2 different label sets. Okay, we did this test in the 3 bands. The procedure is essentially the same that I described earlier. And then we, since we have 10 independent tests each time, we need to decide at the end if a source is an AGN or not. And so we decided that an 8 out of 10 threshold is reliable, is not too restrictive, okay, and is also quite reliable. So based on this, we confirm from the intersection of the results in the 3 bands, 58.3% of our sources. Okay, at this point, we did the same thing that we had done earlier. So combine the 3 bands, but optimizing the selection in each band for obscure AGN. So in each band separately, we identify the set of features that seem to give the best performance in terms of selection of obscure AGN. And you see some features, 8 features, are present in each band. So we also see that most of them are colors. Some features are present 2 out of 3 times. I'll go back on this color issue, okay, in a while. And so based on this, these are the results that we obtain. Here are the various metrics, but what matters is that we are able to find 72.9% of obscure AGN, which is definitely a much better result than what we had in the past. And we are confirming these sources by 3 bands, not just 1. I wanted to mention that colors, we know, are dramatically important. Okay, so one could think, why don't just use colors and don't go through all the pain that comes from light curves and the study of variability? Well, we tested what happens using only colors in this classifier here in the bottom line, and you see that the performance basically drops. Every metric drops. And in particular, for obscure AGN, you get almost 20% less. So even though we know that colors are fundamental, and it's crucial to combine them to optical variability to find AGN, we know we cannot just use colors because that would give us poorer results and also higher contamination, which is something we already proved in the past. So these are my take-home messages, but I think I can stop here, and I'll be happy to take any questions if there's more time for that. Thank you.
Questions?
Thank you. Very nice talk. For the ones that are optically variable and are obscured AGNs, how certain are you that these are actually truly obscured AGNs? I'm thinking of a paper by Aaron Barth from quite a while ago where he looked at a bunch of type 2 AGNs that were optically variable. And when you actually look closer, they have faint broad lines, so none of them were true type 2 AGNs. So have you thought about that at all?
That's an interesting question, and we've been asking that ourselves because, you know, the classification that we base this work on is from a paper from 2016, and is based indeed on the lack of broad lines. But what we thought, okay, we are not 100% sure, okay, we should trust that work on that. But what we thought is that we might ask for time for spectroscopy follow-up, at least of the most intriguing sources. So we wanted to have a look at the spectra, a closer look at the spectra now, because okay, I do have some expertise in spectroscopy, but not that much to be sure. I mean, I would trust them more than myself on this, but I think we should apply for serving time for that. And because also, in principle, they could have changed in the meanwhile. So the data are not contemporary to the spectroscopic observation. So that's a very good question. Thank you.
And there was a question over here. Yes, no? Yes.
So given that you're doing imputation on your magnitudes, so you're going to be introducing a greater statistical error into your colors when you're doing that, therefore. Have you thought about looking at probabilistic random forest instead of regular random forest to see if that improves your overall accuracy?
No, but I think we discussed this when we were in Napoli a couple of years ago at the astroinformatics meeting. Yeah. Is that possible? No, I mean, I didn't look into that yet, and that work is gone, but should I work again on imputation? I mean, I'm not very fond of this imputation process. I mean, it didn't give anything striking, but the last part, I think I had to try because you don't know before.
But I mean, the problem with the imputation is you're going to increase your systematic error, particularly on color, because. So I'm wondering whether color variability is the thing to do.
Okay, I see.
So I just wanted to follow up about the obscuration. So when you look in X-rays, about 20% of things without broad lines are not obscured in X-rays. So whether you call them true Seyfert 2s or not, they may have a broad line region, but the UV is probably dead. And so the key thing is that the SED is very different.
Yeah.
Any other questions? Online? No? All right. Let's thank Demetra again.
Okay. And I did so. Thank you.
Good to go? Yeah. All right. Nevin?
Okay, hello everyone. My name is Neman Kaplar. I work for Rubin Observatory half of the time. I'm a member of system integration and commissioning team. I work a lot of pipelines along with James, for instance, and I'm very happy to talk more about that. The other half of the time I work for Link Frameworks, which is an initiative by Schmidt Sciences to make scalable software for astronomy. And today I'll be talking about this effort, that effort, and I will be talking about the project that we call LSDB, which is aimed to enable AGN science. Not just AGN science, but for this purpose, AGN science. So I'll give like a broad overview of the whole package, and then at the end, a little bit what we do with regards Rubin data, and then as you might have heard in the afternoon, we have a lot of notebooks and tutorial that I invite you to attend. Okay, so basically what is our software and why are we building it? I think this is a good example. This is an example from one of the students at the University of Washington where he found these very interesting Dipper stars. So it's a main sequence stars and they have these quite large dips and there's not really fully fleshed out explanation for what these dips are. He found this in ZTF. ZTF is a relatively small data set compared to what LSST will be. So basically, how do you want to do this analysis instead of a billion objects on like tens of billions of objects, and how will you be able to find these? So that's basically our main purpose. How do we analyze the whole data set at once and we make that accessible to a normal scientist? Basically, the key functionality that we want to enable is to analyze catalog data at scale. Again, when we talk about Rubin, it's a photometric survey with optical, and you want to be able to cross-match and interoperate with the data from other surveys, as we already saw today. And you want to be able to do distributed computation, and I will show you how we use the spatial structure basically to help with these searches and statistical computation. To do this, we have something that I hope that you don't have to learn too much about, but it's called HATS, Hierarchical Adaptive Tiling Scheme. It's a way that we store catalog data in order to enable this sort of scaling. So it enables distribution of large catalogs by catalog providers with hopefully little unnecessary overhead or complexity. There are two basic prongs that we do in order to enable this. One is the directory structure, which is, we have this special directory structure in the way how we shard the data, which is sharded using basically HealPix model, which you might be familiar with from cosmology. And then we use Parquet. Okay, I will just briefly elaborate on that. So how does this work? So this is Gaia. And it's obviously an all-sky survey. And then when we partition the data, we partition it in such a way that each of these partitions has approximately the same number of objects. And this enables very efficient cross-matching and parallel analysis, basically because each of these shards is approximately the same size. So when you want to parallel analyze it, each core can get approximately the same amount of the data.
So you see what happens is that when we go where there's more data, like in the galactic bulge here, we basically need to go deeper. We keep splitting until in the galactic bulge, you see we had to do 7 of these splits that you get the same amount of data as it's on the extragalactic plane. This is the ugliest slide of the presentation, I promise. But basically, how does it work is that you have a directory, and all the data is stored in these directories of a given Hill-Pix order. And then we have a lot of syntactic sugar kind of around and metadata, which enables you to quickly access the data and enables cross-matching. And the data is stored in Parquet. Why Parquet? So because it's open source, it's very efficient, it's column-based access. What does mean, which is so Rubin object data, as you already noticed, has 1,300 columns. You probably don't want to be working with 1,300 columns. You want to be working with a much smaller amount of columns. Parquet enables you that if you know that you just need 3 columns, 4 columns, you can just read the 4 columns instead of having to load all 1,300 columns in memory, and it's highly compressed. Okay, so I talked quite a bit about this structure. This is all just a mechanism that we use to enable this cross-matching and analysis. And on the top of it, we have a LSDB, which is user-friendly. You will be the judge of that. But, framework which we hope that you even enable you to work with this catalog data. The goals of this is, again, to enable the straightforward all-sky and time series analysis, that you can cross-match with large catalogs, that you can use it not just on, cloud, but also on HPC systems, local compute, without a lot of setup. And then, basically, the way it works natively with these catalogs that I presented. It works natively with pandas-like analysis, with a large number of cores, and then it's integrated with something which we call nested pandas. It's basically, if you, for instance, work with ZTF time series data, you know that the data, the observations, the light curves are immediately connected kind of with the objects. So for instance, the Rubin data, it has objects, and then it has what in Rubin world is sources, detections. It's a different object or different table. So when you want to do time series analysis, you basically have to do this joining step first. So we try to enable you that this joining is pre-done for you, and then there's a simple API that you can work with, which I hope to showcase. Okay, just a little bit more about what we've done already with this project. We worked with a lot of precursor data, and these are basically a list of the catalogs that we have worked for or we have in this CATS format. So, it's Gaia, but you see we have DESI, Euclid, Pan-STARRS, different SDSS, different ZTFs, 14, 20, 22, 23, Zuber, and all of these. And these are all available here, and you can use it for research. I want to talk about our main collaborators. Our main collaborators are IPAC and Space Telescope in NASA agencies basically in USA. Space Telescope, for instance, is providing Pan-STARRS, and they will be, I showed you all of these catalogs. We are working with them to move all of these catalogs into the cloud, into their open space buckets. And they are our main collaborators towards providing Roman data in this format. IPAC in Pasadena, they did a lot of work, for instance, verification that the data that you put in is the same as the data you get out. They implemented what I call database-like API, basically TAP queries, which we are trying to provide. And then they are providing Euclid's, Wikidata, and other catalogs. They are our main collaborators within Fornax. Fornax is a NASA initiative to basically do what is Rubin Science Platform, but NASA. Basically, it's Rubin Science Platform. We work a lot with CDS in Strasbourg. Huge catalog provider. They are our main collaborators in IVOA. IVOA is this global organization for virtual observatory, basically that tries to do the standards, how to distribute the data, people who define TAP, who define ADQL, and things like that. I would also like to mention collaborators like S+ in Linea in Brazil and Canadian Astronomical Data Center, who are also providing catalogs and giving code contributions. Regarding Rubin, what we have done with Data Preview 1, for people who, for scientists, the biggest interest is we have the EP1 data on Rubin Science Platform. Soon also, I hope with Canadian IDEC, Brazilian IDEC, we have the data. We have it also in the dark energy collaboration on their compute systems on NERSC. And then we have here, you see, this is the website. We have these different cross matches also with direct cross matches to ZTF, Euclid, and Pan-stars. And then we have also photometric redshifts data, which has been done by the dark energy collaboration, which people can access if you're a data right holder. Very briefly about the future, we are actively running weekly reruns by data management, and we have been doing that for a while. So if you look at here, it says, weekly 25, 10, 11, 12, 13, 14. Basically, data management team every week tries to do a rerun with the new updated pipelines. As soon as they do that, we import it into this HATS catalog that I was talking about. In that way, we often see issues because we are usually the first people who actually test the data, and we are actually participating in commissioning, and I'm trying with, we are using these tools to contribute to the commissioning of the telescope. My aim is to have data preview 2 and data release 1 data available immediately via this HATS format with the Rubin Science Platform and IDEX as soon as the data gets released. Almost the end, basically, I wanted to have this slide as well, which a little bit shows the sizes of future catalogs. So DTP1 is roughly 25 gigabytes. So you see, then it will start increasing. The DP2 is already, if you look at just the baseline, and then I made these different assumptions of various kinds, but if you look at the baseline, the catalogs for DP2, we are talking about 20 terabytes, and then data release 1, again, roughly 20 terabytes. If the data release 1 will not necessarily include the data from DP2. What you can see is that only around DR3, basically, you're starting to go around 100 terabytes. Then it will really start to be difficult to work with the whole data set at once. But I think at least for 1 or 2 more years, we can operate on these scales. Like ZTF is roughly 10 terabytes. We are on that scale of data. All right. The final slide, I wanted to talk a little bit, as we mentioned, we have this tutorial hackathon or demos for the afternoon. I wanted to advertise that just a little bit. The way that I imagine is, so okay, we have this presentation now. We have like 3 hours. At the beginning, I was hoping to maybe go through these guided notebooks, and then towards the end, depending on the interest, we can do some free coding time. We have 5 notebooks. I put here topics from the first 3, which will be basically, how to load these catalogs, how to perform cross-matching. Then I will talk about these nested pandas. And then notebook 3 will be the photometric redshift catalogs. Then 4 will be maybe more complex workflows. And 5 will be like AGN workflows. At the end of each notebook, we have like problems, which I have solution in the separate notebooks, which I hope that people can work with. So basically, if you want to figure out how to get to all these fascinating plots, then I invite you to join in the afternoon. Okay, and that's all I had. Thank you.
Questions?
So how does this work, like alongside table access platform? I guess my question is will we move to this from table access platform? Is this more efficient, or will they work alongside each other, side by side? What's the plan?
That's a very good question. A little bit of background even. First attempt that we tried to enable time domain astronomy and LSST, we had something which we call tape, and it had object and source tables together, and then I tried to join on the fly and remember what filtering you have done, and that was just very, very difficult. This attempt now is because we think this is more user-friendly. From the observatory side, I don't think we will move away from objects and sources, because the data management, that's what is the output from the pipeline, and there is no way that we will move from that. It's just way too complex. My hope is what I have talked even with Bob Blum and others is that we will be like an official side product exactly, because ultimately the amount of data that we are discussing, and that's why I showed the slide with the size of data, that it's actually not that big. It's actually, we are talking about, University of Washington now has 1.5 terabytes or petabytes, which is like size of DR11. Exactly.
Thank you.
I think we saw a question online.
Yeah, hi. Thanks for the talk. Maybe you touched already, not exactly your talk, but somebody before. Unfortunately, I had to miss a couple. When you were mentioning IPAC, I didn't hear any mention of SpherX, and they are observing practically the same time of LSST. So I was wondering whether there is already an agreement in place for combining LSST and SpherX.
Yeah, I am not familiar of such efforts. Having said that, Gregory Dubois-Feldman, who is like a person at IPAC, who is also one of our main contacts there, he's, I think, like chief lead scientist for SpherX and also like chief lead or something for Rubin. So I would be surprised if there is nothing because it's the same people. Having said that, but yeah, I don't think there is no plan, right? So Matthew says, I haven't heard anything as well. Exactly. I'm not sure why, but there might be better reasons. Matthew will say something.
Yeah, no, I mean, just as a Caltech person.
Yeah.
I mean,
at Caltech, they don't talk to you.
I have lots of IPAC friends.
Yes.
No, I mean, IPAC has a lot of trouble at the moment anyhow, but it's nothing is planned as far as I've heard. Yeah. So I don't think it's on their radar.
We should try to bring it up.
I think, I mean, again, and Matthew can stay more, like Gregory must, if it were feasible, he must have been doing something, right? It's the same person.
Yeah, but it's a lot of work, and unless there is a strong requirement for it, then people need physically to move on with their life. So I also understand why it is not done. So we should discuss how important will be, which I think it is, especially for the variability. We should make a request to combine the data.
And I could even say, Euclid is obviously such an amazing synergy. And again, it's IPAC is the USA host. And you see, that's also like...
That is different, right? Because it is Europe. So there is already an LSST Euclid agreement for certain projects.
Right,
I see it more complicated. But I think SpherX and LSST should be easier to handle.
I'm just pointing out how complicated it is. I'm just agreeing with you. Yeah.
Thanks.
I think I saw a question online also that will the notebooks be available to remote attendees?
Yes, yes, I think you can run them now because it's on Rubin Science platform, and you should just be able to run them like now. Yeah.
Any other questions? All right, let's thank Nevin again.